If you fall into a black hole, the intense gravity will stretch your body out like a long, thin noodle. It is the most famous, visceral death scenario in all of astrophysics. The specific term spaghettification was popularized by physicist Stephen Hawking to describe exactly how extreme gravitational tidal forces would tear a human apart. But this terrifying hypothetical requires a specific set of conditions to actually happen. Namely, the black hole in question has to be sitting perfectly still, generating a completely non-rotating gravitational field. While dying as a noodle makes for great science fiction, that scenario relies on a simplified mathematical model. In the actual universe, a perfectly stationary black hole almost certainly does not exist. That simplified stationary model is called a Schwarzschild black hole. It has mass, but absolutely zero spin. If you fall into one of these theoretical voids feet first, you encounter extreme tidal forces. Because you move closer to the center of mass, the downward pull on your feet is exponentially stronger than on your head. To maintain your overall mass under this extreme differential, you are simultaneously stretched vertically and squashed horizontally into a thin strand. But as this radio image of the supermassive black hole M87 star shows, real astrophysical black holes are surrounded by glowing, asymmetrical accretion disks. That asymmetry tells us these massive objects are violently spinning. When you introduce rotation into the mathematics, the rules of spaghettification no longer apply, ensuring a much stranger fate for anything falling inside. To understand what actually happens, physicists use a different mathematical model called a Kerr black hole, which accounts for realistic rotation. As a Kerr black hole spins, it drags the very fabric of space and time along with it. This extreme rotation generates massive outward centrifugal forces that actively fight back against the inward crush of gravity. That centrifugal pushback is so strong it creates a second, smaller boundary inside the void, known as the inner horizon. The space trapped between the outer event horizon and this inner boundary is a region of extreme instability, where the inward pull and outward push reach a mathematical stalemate. This hidden internal structure is the physical mechanism that enables the massive radial compression found in rotating systems. Imagine our astronaut falls feet first past the outer event horizon, descending rapidly toward that turbulent inner boundary. Because of the intense centrifugal forces pushing outward, the tidal vectors suddenly flip. The downward pull at their feet becomes weaker than the downward pull at their head. The space around the astronaut rapidly decelerates, compressing them from top to bottom, while stretching them outward from side to side. Physicists call this radial compression pancakeification. It is the true signature effect of crossing a Kerr black hole's inner horizon. A black hole's spin dictates the exact geometry of the gravitational forces inside, acting as the ultimate decider between dying as a long, thin noodle or a flat, wide pancake. But semi-classical quantum physics introduces a final, lethal complication. An astronaut would never actually survive long enough to reach the pancakeification stage. As matter and energy fall inward, the intense centrifugal forces at the inner horizon cause them to pile up and compress in a phenomenon called mass inflation. This triggers a blue shift instability. Quantum particles are compressed so tightly that they generate an exponentially dense, infinite wall of radiation and negative Hawking temperatures. Long before gravitational tidal forces could flatten an observer, this concentrated wall of extreme quantum energy would simply vaporize them on contact. Let's pose a final thought experiment. Suppose our astronaut is magically indestructible and manages to pass straight through that radioactive firewall. What happens next? The extreme concentration of energy inside the inner horizon causes the local space-time itself to back-react, triggering a violent series of geometric bounces. The indestructible observer is tossed through a rapidly shifting gravitational field. They are squashed flat, then stretched tall, alternating rapidly between pancakeification and spaghettification. This chaotic cycle accelerates as they fall deeper, finally ending when they strike the space-like singularity at the dead center, a point where the laws of physics entirely cease to function. Spaghettification may be the more famous story, but the physics of a spinning black hole reveal a much more chaotic reality, one defined by infinite radiation and alternating tidal crush.